Welcome to the first problem set, Crouching Basic in Acid Part 1. In this video, we're going to explore a few different types of acid-base problems. All of the problems have been separated by type, so I'm going to go through them in sequence by the different types. Let me launch straight into the first type. I should mention that I'm going to make use of some concepts and techniques that I discussed in the prequel. So some ideas here, well, it might be useful to watch the prequel first. So let's talk about type 1. By the way, the naming is mostly arbitrary. I could have called anything part 1. Type 1, I mean. Okay, so what are these type 1 problems? They are a type of excess problem where you have a reaction. Let's call it, say we have a reaction A plus B goes to C plus D, and I'm going to keep, actually, it's no good, I need some more space on the left hand side. This is a type of problem where, say you are given a beaker where you have some solution of A, and you allow it to react with B. And then, as I discussed in the prequel, we can say that the solution A has an initial state, and we will characterize the initial state of A with the initial moles of A. And then let's say you add some of solution B to the beaker, and a reaction starts. And in that reaction, you use up and you lose some of the moles of solution A. So let's say that this here represents the moles of A that react. Those are lost to you. They, along with B, become the products, C and D. And this piece here, let's say that represents the moles of A in the final state. That's what you're left with. That's the excess. So in this problem type, A is in excess, B is the limiting reagent, so all of B is used up. And then mathematically, what we can write is that this one is related to the other two by the following equation. The moles of A that react are simply what we start with minus what we are left with. This is what we lost. That's how you can find the moles of A that react. Now, I said in the prequel that this can be understood, or this can be described quite well using the same format as you have for for equilibria, the equilibria rise tables or ice tables. So let's borrow that. Initial moles, change in moles, final moles. Okay, so I'm about to describe the problem type. In this problem type, you're given the initial moles, or you're at least given some way of figuring out the initial moles of a reactant A. And there is some way, there's enough information to calculate the final moles. So you have the initial state, the final state of A, and the question will be about this one. The moles of the limiting reagent will be something to do with this, like either the initial moles of the limiting reagent, the initial mass of the limiting reagent, or the solute of the solute that is dissolved to make the limiting agent solution. Maybe it's the initial concentration of the limiting reagent. Either way, it relates to the initial state. Okay. So in these types of problems, the way to proceed is, of course, to identify that you have this type of problem. And then you go and calculate this number. You go and calculate this number. So once you have this one, using this equation here, you can go and calculate the change in moles. That would be the moles of A that react. And as you know from equilibrium, this is the only line in this table, the change in moles line. This is the only one that you are allowed to mole ratio. So then you can simply mole ratio this to here. You get the moles of B that have reacted. And once you have the moles of B that react, you can go to this line, because of course the moles of B that react is the initial moles, because you're left with nothing here. It's the limiting reagent. Let me just say something about this side of the table. In these problems, we don't actually look at them. They're not, they aren't interesting, or there aren't any problems that really look at those. So we ignore them. You have zero products initially, and then everything that you form just comes from this line. So if I were to write something, although, like I say, you're not going to see problems that are really focused on them. The mole ratio from A to C is 1:1, from A to D is 1:1, hence these numbers. I should say you gain here and you lose over here. Right, I chose the coefficients to be 1, 1, 1, just for simplicity's sake, but they don't have to be. So that's the first problem type. As I said, you're given these moles, or you have some way of calculating those moles. You have some way of calculating these moles. You then take the difference between the two, as shown in this equation here. That gives you moles of A that react, and then your mole ratio, you get the moles of B that react. That's equal to your initial moles. Conceptually, that's the problem. Okay, so let's have a look at an example. Let's begin with the first problem of the type that I've just described. We have two questions here. 731 for 3 marks, and this 732 for 7 marks. We need this one. We need the information in the earlier problem for the later problem. So let's have a crack. So we're told that the water in a certain lake has a pH of 5. And for 3 marks, calculate the concentration of hydronium ions in the water. I did mention in the prequel that the pH is a way of giving the state of a solution, because we can work backwards from the pH to find the concentration. So this is our initial measurement of this lake as a pH of 5. And I also discussed the way that we can take the pH and convert back to the concentration of hydronium ions. So let's do that now. The way to go backwards is the following. It's this concentration is 10 to the power of minus the pH. Let's write it like this. It's a concentration, so this is the units. Okay, done. Now we're told the volume of water in the lake is 4 times 10 to the 9 cubic decimeters. Lime calcium oxide is added to the water to neutralize the acid according to the following reaction. This calcium oxide plus 2 hydronium ions goes to a calcium ion and 3 water molecules. If the final amount of hydronium ions is 1.26 times 10 to the 3 moles, calculate the mass of lime that was added to the lake. Right, so we're given the volume of the actual lake, and we're told now, given some final information, it's about these hydronium ions again. So let's take stock of what we have. We have this information, which we've used about the pH, and this relates to the initial state. And you perform some reaction, and at the end of this reaction, you still have some hydronium ions left over. This many moles. So clearly the hydronium ions were in excess. That's why, and we're being asked about the limiting reagent, the calcium oxide. That's why this problem is of the type that I described. So let's use the table so that we can see what information we have and what information we still need to solve this problem. So we have enough information to calculate the initial moles. We have that the concentration is this and the volume is this. So in principle we know this number. And we have that the final moles is this. So we can see clearly that we have enough information to calculate this number, the change in moles of hydronium ions. If we can get this number, then we can mole ratio across to this one. Why would we do that? It's because we seek information about the calcium oxide. We are looking for the mass of calcium oxide that we had initially. This is the limiting reagent, so we have nothing at the end. And so whatever our change in moles is, must be equal to this number. So we start with this amount of moles. We lose everything here. So let's write it like this. That's how we get 0, because it's the limiting reagent. So again, we're going to calculate this number, mole ratio here. Let's take note, there's 2, this 1. We find x, and then we can get the mass. Okay, so clearly we need to start here. So let's write that. We need the moles of hydronium ions, initial. That's what we're going to get now. We're going to use the formula C equals N over V to find the moles. C is 1 times 10 to the minus 5. V is 4 billion liters. So N is this number. And now we're going to use the equation. The moles that reacted is equal to the moles that I had at the start minus the moles that I'm left with. The initial moles is this number. The moles at the end is this number. And that gives me, I can have a look at my calculator, it gives me 38,740 moles. So now I can put that in over here. I suppose I can put this figure in as well. Of course, these are moles that I lost. Now I mole ratio this number over here. It is 2 to 1. If I divide this number by 2, we get this is 19,370 moles. I am aware that this is quite a lot of writing out. I don't expect you to do the table as well. as all of this writing out that you see below the table. I am putting this all in because I think it's instructive to see how the different quantities relate, but also to identify what type of information belongs to the final state, what type of information belongs to the initial state, based off the language used um, in the problem, to really hammer home this idea that we need to find the change in moles, and only then can we mole ratio. Right, though, almost done. So now that we have the moles of the calcium oxide, we want to find the mass, so let's use this formula. Let's find the molar mass of calcium oxide. This is 40 for the calcium and 16 for the oxygen. So we have 56 grams per mole. Then, if we use this formula, we will get what? It's 1084720, which is 1.1,08 times 10 to the 6 grams. Done. So that's all our working out. Right, let's move on to the second problem. A sulfuric acid solution is prepared by dissolving 7.35 grams of H2SO4 liquid in 500 cubic centimeters of water. We have a 2 marker and then a 9 marker. And the 2 marker is necessary for the 9 marker. So let's start with 721 and let's use this dark blue. So we're given a mass of this H2SO4 and we're given a volume. They want us to figure out the number of moles of H2SO4 present in the solution. Okay, so this is not complicated. We are simply going to use this formula. Let's figure out the the molar mass of H2SO4. This is 2 for the hydrogens. We have a 32 for the sulfur. We have 4 by 16 for the oxygens. And if you plug this into your calculator, you will get 98 grams per mole. Now we substitute. And what do you get? This number. Generally, they want 2 decimal places. So this is the number that I'm going to quote my answer. But this is the number that I'm going to work with in my calculations. So let's just recap. I know the initial state of my sulfuric acid. I have the moles and I have the volume. As I mentioned in the prequel, if you have two of the three variables in the formula C equals N over V, you know the third. So we know everything that we need to know about this sulfuric acid solution, at least initially. We have the initial state. Now they say that sodium hydroxide pellets are added to the 500 cubic centimeter sulfuric acid solution. So this is going to produce a change, of course. They have a change of state coming. And then they give us the balanced equation over here. After completion of the reaction, the pH of the solution was found to be 1.3. Assume complete ionization of the sulfuric acid. So let's pause there. Again, as I mentioned in the prequel, pH is a way of giving a measurement of a solution. And after this reaction, we can see that the pH it's still acidic. We started with an acid and we still end with an acidic solution after the reaction. So again, as I mentioned, this is an indication that the acid was in excess. We had too much acid, that's why we have leftover acid. And I also mentioned in the prequel that we can go from the pH all the way back to we can use that, as you saw in the previous problem, we can use that to find the hydronium ion concentration, and then we can use the ionization equation for the acid to figure out the concentration of the acid. All I'm trying to say is we have the initial state of the acid, and this relates to the final state of the acid. And now let's have a look at the question. Calculate the mass of sodium hydroxide, that's the limiting reagent, added to the H2SO4 solution. Assume that the volume of the solution does not change. Okay, so we can see this is another problem of the same type. And so I'm going to write out the equation again so that I can write in the format of the table. Is terrible handwriting. I actually have this number, so I'll fill it in. Again, I don't expect you to write out this table. I'm just writing it out because I think it makes it easy to see where the figures go, what each figure is, keep track of the time or the state of the solution. Okay, so I'm going to put over here, let's use red. I'm not actually going to put the final moles of the acid. I'm going to put the information that we need to find it. Right, and then what are they asking for? They're asking something about the sodium hydroxide, the mass. And that would have been an initial mass, because of course we don't have anything at the end. It's the limiting reagent. So the change in moles must have been X. So again, we're going to calculate this number. We already have this one. Once we get the difference, the initial, the big one, minus the smaller one, that's going to give us this number over here, and then we mole ratio to find this number. Once we have x, we can go and calculate our mass. Very similar to the previous problem. The only difference is really the way we find this number and the way that we found this number. That's the only difference. Okay, so let's go and calculate the final moles. This is going to be it's going to be an involved process. There's a few steps. Okay. So we start with the pH. And then so our hydronium ion concentration is, and this gives us, I'm going to write 4 decimal places. Now, as I mentioned in the prequel, anytime we have information about the hydronium ion or the hydroxide ion, but we are really interested in the acid or the base, then we can go backwards to the acid or the base using the ionization or the dissociation equation. So we need the ionization equation for this acid now. Remember, it's H2SO4. The ionization equation is not going to get you any marks, but the mole ratio from the equation is going to get you marks. If you feel like you need to write it out, then write it out. If not, simply perform the mole ratio. Well, in this case, it's a concentration ratio. So here's your equation. Any acid reacts with water to donate its acidic hydrogens by passing the hydrogens onto the water, and it produces hydronium ions. We have 2 acidic hydrogens, so we need 2 water molecules and we'll form 2 hydronium ions. This is a feature of all diprotic acids. So we can write the following. It is 2 to 1. So this concentration here I'm actually taking the entire, I have the whole number written out in my calculator. I'm just going to divide that by 2. So I'm actually not working with just 4 decimal places. Then I write this out. 0.0251. And let me just put the unit. Right now I have my concentration for the acid. It's still not the moles, but I can use the volume now. So let's use C equals N over V. Let's write in the concentration that we just found. So N is just the product of those two. I'm going to use the whole number now that I've still got on my calculator screen. My volume was 0.5. Let's check that. So the number of moles that I get is 0.0125 mole, and it is for H2SO4, since this concentration was for H2SO4 and the volume was obviously for H2SO4. Okay, so I have my number of moles now for the acid in the final case. So let me write this in. 0.125. Okay, so now I'm going to take the difference. I'm going to say this one minus this one here minus this one. That'll give me the change. Let's write that. The moles of H2SO4 that reacted is equal to the moles of H2SO4 that I had in the initial state minus the moles of H2SO4 that I have in the final state. That is 0.075 minus 0.0125. What does that give us? 0.0625. Is that right? Yes, 25. Mole. And of course it's H2SO4. 0.0625. Where does that go? Here. And now we can mole ratio here, and we can get X. Other mole ratio step. And that was 2, no, it was 1:2. So I just have to double this now. And that gives me 0.125 moles. Remember, so now the question was asking us for the mass of sodium hydroxide. We have the moles, so we can just use this formula now. Let's actually calculate the molar mass. Over here, the molar mass of NaOH is 23 for the sodium, and 16 for the oxygen, and 1 for the hydrogen. So what does that give us? 17 euro plus, so that's 40 grams per mole. So M is the product of the two. Okay, so we're done. 5 grams. Again, that's quite a lot of work. I am including probably more detail than you would. Again, I said this is not necessary. If you can see the step, you can just go directly to the step. Just make sure you don't like. So the reason that I'm writing this out is because I don't want anyone who watches to get the 1 and the 2 mixed up, and then get the whole thing wrong just because of that mistake, which is it's easy to make. But it's a big question, and that's why it's for 9 marks. Okay, so we carry on. Another problem of the sort. Let's see. Hydrobromic acid reacts with zinc hydroxide solid according to the following balanced equation. An unknown quantity of zinc hydroxide is reacted with 90 cubic centimeters of hydrobromic acid in a flask. Assume that the volume of the solution does not change during the reaction. Okay, so all we're told so far is we got some solid reacting with 90 cc's of some hydrobromic acid solution. And then the excess hydrobromic acid is neutralized by 16.5 cubic centimeters of sodium hydroxide of concentration 0.5 moles per cubic decimeter. The balanced equation for the reaction is given. Okay, let's stop there. As I mentioned in the prequel, sometimes you're given some solution and it has some initial state, but then it changes its state because you perform a reaction like we have here. It's a very funny star. You get the point. See, our hydrobromic acid solution evolves because of this reaction. And now we're given a second reaction. This one. This is exactly the kind of reaction that I mentioned in the prequel. Its only purpose is to serve as a measurement of the solution, of the hydrobromic acid solution, after the reaction. So whatever we get from here, all we're thinking is this reaction's its only purpose is it's a measurement device. This is the primary reaction over here. This is secondary. Right, so first off, calculate the pH of the HBr solution remaining in the flask after the reaction with zinc hydroxide. Right, so one thing to note, we asked for a pH, and I did mention in the prequel that this depends on obviously which was in excess. In this case, they're talking about the HBr solution after reaction with the zinc hydroxide. Right? We know that the HBr, well, I mean, it's stated in the problem, HBr is in excess. So we just need to figure out the concentration of HBr that remains, and then we can then figure out the hydronium ion concentration using the ionization equation. So that's going to be the strategy. If we come over here, we're given a volume and a concentration for this base. That is enough for us to calculate the moles of the base. And this was a neutralization reaction, so whatever moles of the base we have, we can simply mole ratio that to the HBr, and that'll give us the moles of HBr that reacted, that we had left over after the primary reaction. And then we can just get the concentration. You could use the titration formula, and I do actually want to use the titration formula here, but I'm not going to use it because simply because I know someone who was told not to use it by their teacher. Okay, so let's have a go. We're calculating the moles of sodium hydroxide. The concentration was 0.5 moles. We don't know. The volume is this number. So our calculator tells us okay, there's our sodium hydroxide moles, and now we're going to mole ratio. That is 1 to 1. So these moles here, you still get a mark for showing this, even though it's not complicated. Okay, and now let's get the concentration. That's not what I meant to write. What volume? The pH of the HBr solution remaining in the flask after the reaction here, right? So after this reaction with the zinc hydroxide, we still had a volume of 90 cubic centimeters. Don't use the 16.5. That was the solution of sodium hydroxide, the volume for that solution that we needed to neutralize our HBr solution. But we're interested in the pH of the HBr solution, whose volume was 90 cubic centimeters. So we do the calculation in our calculator, and I get okay, that's my concentration. And then remember, we were asked to find the pH of the HBr solution. This is the concentration of HBr. Now the ionization equation is this. In the problem that I got this from, they started out by telling us that HBr is a strong acid. I didn't include that part, but the fact that it is a strong acid is what enables us to do what we will do now. If it's a strong acid, then it ionizes fully, and then only because of that we're allowed to say that the concentration of HBr to the concentration of H3O plus is 1 to 1. So this concentration here is the same as this concentration here. And now we can use our pH formula. I still have this number in my calculator, so I'm just going to take the logarithm of that. And I end up with 1.3. Sorry, that's not 1.3. It's 1.04. And it's a pH, so there's no unit. Okay, done. Now for 6 marks, calculate the mass of zinc hydroxide initially present in the flask if the initial concentration of HBr was 0.45 moles per cubic decimeter. Okay, so let's take stock of where we are. This step here in 731, although the aim was to get us to calculate a pH, we still calculated the number of moles of HBr that remained after the reaction with zinc hydroxide. So that gave us the final state of the HBr solution. And now we're given an initial concentration, and we still have, well, the volume of HBr initially, I mean, it never changed. It was always 90. In the initial test state and in the final state, it was 90 cubic centimeters. So we have an initial state, and well, we had our final state, and now we're also given the initial state. So I will write out the reaction. Goes to Zn Br2 plus H2O, and then just check that this is balanced. We need 2 of these. F 2 bromines, 1 zinc, and then we need a 2 over here. Okay, so not sure what happened. Okay, and then change in moles, and then final moles. The question is asking the mass of the base, the zinc hydroxide. It was the limiting reagent because we know that the HBr was in excess because they asked us to calculate the final pH. So this is going to be our X. Final moles of the limiting reagent is 0. HBr initial moles that we're going to find out now, but it comes from our concentration that they told us was 0.45 moles per cubic decimeter. They said that there. And the volume was 0.09 cubic decimeters. And the final moles, we've already calculated that. Was that which we found there. Okay, so clearly I just need to go and calculate the moles here from the figures that they gave us. And then we can calculate the difference, and then we mole ratio that to here. Okay, so we just need to use this formula now. C equals N over V. And we go to our calculator. And I get 0.0405 mole. And who is this for? It's for HBr. And now that was the initial moles. And then we take the difference. So I can say that the moles of HBr that reacted is equal to moles HBr initial, which I've just found, minus moles HBr final. And let's fill all of this in. We take that difference and get this number. And now that is this number. 0.3225. Now we look 2:1. So I'm going to mole ratio this now. And this gives me this number of moles. And now last step, they wanted the mass. have the number of moles. The molar mass of zinc hydroxide is, one second, let's pull up. It's 65 for the zinc plus 2 times 16 plus 1, which is 99 grams per mole. Actually, to 2 decimal places, this is 1.60 grams. Okay, done. Next problem. The flask contains 300 cubic centimeters of dilute sodium hydroxide, NaOH, of concentration 0.167 moles per cubic decimeter. And then for 3 marks, calculate the number of moles of sodium hydroxide in the flask. Okay, easy stuff. Let's use this color. So we're given a concentration and the volume. So in our calculator, we get 0.0501 moles of NaOH. That is the state of our sodium hydroxide. Now, ethanoic acid of volume 500 cubic centimeters and of unknown concentration, capital X, is now added to this flask. So we have a reaction to give a solution of volume 800 cubic centimeters. It's the 500 that the 300 that we started with, plus the extra 500. Okay, so we have an initial state for the sodium hydroxide, and then we disturb it. We allow the sodium hydroxide to react with ethanoic acid. And it is now found that the pH of the mixture is 11.4. Okay, so there we are. As I mentioned in the prequel, after this reaction, we measured the solution with a pH. This pH tells us the state. It tells us something about the state of the solution. In particular, we notice that this pH it's basic, it's alkaline. So you started with a base, it would have had a pH of, obviously, it would have been bigger than 7, but it's still bigger than 7. So your base was, of course, in excess, as was mentioned in the prequel. So we see we have an initial state for our sodium hydroxide, and then we have a final state. And of course, the change in state was achieved via a reaction with ethanoic acid. Okay, so the next question, calculate the concentration of the OH minus ions in the mixture. We're going to use the pH, right? Remember, pH tells us about H3O plus concentration, but we can turn that into OH minus concentration using our Kw constant. So let's get the hydronium ion concentration first. It's 10 to the power of minus the pH value. And this gives us a very small number. Let's write out 3.981 times 10 to the minus 12 moles per cubic decimeter. I'm going to store this number in my calculator. I can actually just work with this, but I want to store this number in my calculator. Okay, so now we use this formula, the autoionization of water, to go from this concentration to this one. And at 25 degrees Celsius, which is what we have to assume, the value of this constant is given in the data sheet. 1 times 10 to the minus 14 . So the OH minus ion concentration is okay, there we go. And I might store this value in my calculator as well. That's all that they were asking us for in this 7.2.2, but now the question for 6 marks, they want the initial concentration, not of the sodium hydroxide, because we already have that, but of X of the ethanoic acid. Let us recall that we know the initial state of the base, and in essence we do know the final state of the base. In fact, we essentially just calculated the concentration of the base, and we know how the volume changed. Right, in the final state the volume was 800 cubic centimeters, because we had two solutions, we added them together. Okay, so our sodium hydroxide is in excess, and we're looking for something to do with the limiting reagent. So I'm going to write out the reaction with the ethanoic acid. Need more space here. Right. The initial moles of the sodium hydroxide, I have that 0.0501, and I don't actually know the final moles for the sodium hydroxide. I have essentially about the sodium hydroxide. Recall that in the prequel I said that you can take your OH minus ion concentration and you can go backwards to your base, your whatever hydroxide you had, in this case sodium hydroxide. So I have the OH minus ion concentration, and I have that the volume is 800 cubic centimeters or 0.8 cubic decimeters. So in principle I can find this number, the moles final. Once I get the moles final, I take the difference between these two, I get to give me the change in moles. And once I have the change in moles, I can then mole ratio to the limiting reagent. I started with X moles of the ethanoic acid. I then lost all X moles, so I had nothing left over. That's why, and my base was in excess. That's why we had the pH of 11.4 at the end of the reaction. So this is the strategy. Calculate the moles here using these two numbers, and then take the difference. So we're going to use C equals N over V. Our concentration, where do we find that? Here. So I get that's how many moles of sodium hydroxide I have in the final state. So let's get rid of this. Again, you don't need to write out the table. I'm just using it because I think it is instructive. Makes it easy on the brain. Not only is all of the information that we need to solve the problem summarized very nicely, compactly. These zeros look a bit like sixes. So all of the information is summarized nicely, but also in a manner that is suggestive of the solution. We can see that if we started with this number and ended with that, clearly we must have lost something, and the lost moles is what reacted. So let's take that difference now. The moles of sodium hydroxide that reacted is equal to the moles of sodium hydroxide that we had in the initial state minus the moles of sodium hydroxide that we had in the final state and this was 0,0, I don't remember, 501. These moles that we just found. And this gives us this number, 0.0481 moles. And now we just mole ratio across. You can see it's 1:1. So we'll write moles of NaOH to the moles of ethanoic acid. It's 1:1. So this many moles here would have reacted with this many moles here. Now, what were they asking for? A concentration. So after we found this number, which is this number, we're going to get the concentration. So actually, let me just come here and write that the volume is 0. For the acid, it's 0.5 cubic decimeters. So we are doubling our number because we're dividing by a half, and we get 0.0962 moles per cubic decimeter. To 2 decimal places, this gives us x equals 0,0. Actually, to 2 decimal places, that is. Okay, done. Next problem. Learners add 150 cubic centimeters of a sodium hydroxide solution, NaOH, of unknown concentration to 200 cubic centimeters of a 0.03 moles per cubic decimeter hydrochloric acid solution, HCl, as illustrated below. They find that the pH of the final solution is 2. Assume that the volumes are additive. And then they give us the balanced equation. And then for 3 marks, calculate the concentration of HCl plus ions in the final solution. Here's the final solution. It has to do with this pH, so that's not complicated. That's why it's for 3 marks. But the big one, they want the initial concentration of the sodium hydroxide. Okay, because of course, we only had a volume for the sodium hydroxide. For the acid, we had a volume and we had a concentration. Okay, notice, so we have our initial state for the acid. This gives us the initial state for the acid. But notice that the pH is much less than 7. Right? So the pH, so we have an acidic solution in the final The final solution is acidic, so that means since we had an acid reacting with a base, it means that the acid was in excess. Right? This here, as I mentioned in the prequel, this pH is a measurement of the solution. It's what tells us about the final state of the solution. And recall that they said the volumes are additive. So from the pH we can get a concentration. Together with the volume we can get a number of moles. Okay. So again, this is in excess. And this is the limiting reagent. So let's tackle 7.2.1. We want the concentration of H3O plus ions. Again, we use the pH formula. The pH was 2. So this concentration is equal to 10 to the power of the negative pH moles per cubic decimeter. That is just 0.01. Let's just write it like that. Okay, done. Now 722, the initial concentration of the sodium hydroxide. Okay, again, I am going to try and write out a table I'm going to change this. Let's go for a fountain pen. Okay. The initial moles of the acid, yes, I can find that because I have a volume of 0.2 cubic decimeters and I have a concentration of 0.03 moles per cubic decimeter. Fountain pen is like so much better. And then for the final moles, I have my concentration. Well, I didn't prove that my concentration was this actually, so let me scratch that out. Let's just write I have a pH of 2 and I have a volume. They said that the volumes were additive, so it should be 200 plus 150, that's 350, 0.35 cubic decimeters. Okay, so as we were saying, I have enough information to calculate the initial moles. I have enough information to calculate the final moles. The difference between the two is this number. And then I can mole ratio that number here. It'll give me the change in moles of the sodium hydroxide. 1:1, and then I can get this number. This number is that number because sodium hydroxide was the limiting reagent. And they want the initial concentration for the sodium hydroxide. So let's just write in over here, right, that the volume was 0.15 cubic decimeters. Let's get rid of some of this. The 0 can stay because I like 0. Okay, so what to do? Let's get the initial moles and then we'll get the final moles. Okay, I was just checking what I've already calculated, but this was for the final state. So I've partially done the work for this, but we're on the initial state now. So the concentration was 0.03 moles. What I'm looking for, the volume is 0.2. So that is 0.0. It's 2 zeros and a 6. Okay, and now okay, so we have a concentration of hydronium ions. It's this number. So I'm going to write out the ionization equation because I want to ratio from hydronium ions to the HCl. And now why did I write the equal sign? I didn't mean that. I mean, it's true, but that's not what I meant. Not quite true, it's approximately true. Okay. So this is 1:1, and I have this concentration was 0.01 moles per cubic decimeter. So this concentration is 0.01 moles per cubic decimeter. And now I can go and calculate the number of moles using the concentration formula. This. Now, what was my final volume? 0.35. And it has to be the final volume because this concentration came from the pH, which was it was a final quantity. So 350 cubic centimeters. Then N is equal to 2 zeros. Could have predicted that. Okay, moles of what? HCl. Okay, so we have the initial moles, we have the final moles. Now, if we have a look at our table, we have this number, we have this number. They seem to have changed color. We're going to calculate the difference. The initial was this number. The final was this number. So we have 6 minus 60 minus 35 is 25. Yep. And then we can mole ratio now. We're going to mole ratio from year to year. And this number is this number. So we may say the following. We were interested in the concentration for the sodium hydroxide. So I'm going to say, well, first I have the mole ratio. I can't just calculate the concentration. We're going to get a mark for the mole ratio. So we need to say moles HCl to moles NaOH is 1:1. So this number here gives us this number here, and then C equals, that's moles N over V. But the volume, they wanted an initial concentration for sodium hydroxide. That's why we wrote this volume here, 150 cubic centimeters. And this gives us, almost done, 1/60, 0.0 to 2 decimal places and get it 2 moles per cubic decimeter. Okay, done. It looks like it's quite a lot of writing out, but honestly that's just because I've been writing big. Okay, let's move on to the next problem. Okay, household vinegar contains 4.52% ethanoic acid by volume. A 1.2 gram impure sample of calcium carbonate is added to 25 cubic centimeters household vinegar. Okay, so these are the two reactants, ethanoic acid and calcium carbonate. On completion of the reaction, the excess ethanoic acid in the household vinegar is neutralized by 14.5 cubic centimeters of a sodium hydroxide solution of concentration 1 mole per cubic decimeter. The balanced equation for the reaction is, and they give it to us, and then we have a 3 marker and an 8 marker. Calculate the number of moles of unreacted ethanoic acid, and before I get into the next part, let's just go over what we know so far. So let's change color. We have a little bit of information about this substance, and then we have impure, so we can't actually do anything yet with this 1.2 grams of the substance, and we're given a volume for the vinegar, for the ethanoic acid. And then they tell us that on reaction, the excess ethanoic acid in the household vinegar is neutralized by blah 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 blah. Okay, so this information here, this is our measurement. The primary reaction is with the calcium carbonate. This is the secondary reaction with the sodium hydroxide. This is our secondary reaction here. This is the primary. You write it like this. Okay. So this measurement here is simply telling us about the final state of the ethanoic acid. I mean, I'm not yet sure if this problem is of the type that I described, but however we proceed, or whatever happens in the rest of this problem, we are sure that this measurement gives us the final state of the ethanoic acid. That's what we're thinking at the moment. Okay. Now let's see. Calcium carbonate. Of course, we are going to attempt this problem first, but this is a 3 marker. It relates to this paragraph that we just spoke about. Let's read what they're asking in the next question. Calcium carbonate reacts with ethanoic acid according to the following balanced equation, and they give it to us. Calculate the percentage calcium carbonate in the impure sample if 1 cubic centimeter of household vinegar has a mass of 1 gram. Okay, so there's a couple of weird quantities here, but if you just think about it a little bit, it'll start making sense. This and this, that's a bit, okay, that's enough information to give us a density, which is not exactly a concentration. It's kind of like a concentration, but you can see it's a volume and it's a mass. Here we're given information, percentage acid by volume, and here we're given a volume. So clearly this piece of information can go with this piece of information, right? And these relate to the initial state of the acid. So what we're going to do, if I can get rid of my scribblings, well, what we're going to do is we're going to put the relevant pieces of information together. Actually, you know what? First, let's do 7.2.1 before we get too far ahead of ourselves, and then we realize that we need to do this first. The number of moles of unreacted ethanoic acid, that's leftover acid. And how are we going to get that? Well, they gave us a concentration and a volume for the sodium hydroxide. So we're simply going to calculate the moles of sodium hydroxide at a Vig to mole ratio. The concentration was 1, the volume was 14.5. And now we need the mole ratio. Okay. Now, we were saying household vinegar is 4.52% acid by volume. There's the volume, right? So we're going to get the initial state. Of the acid. First we get the volume like this. Okay, so there is the volume. And now, later on, they tell us 1 cubic centimeter of vinegar has a mass of 1 gram. So we're going to turn this volume into a mass now. So 1.13 cubic centimeters is to 1.13 grams. Okay, so now we have a mass of ethanoic acid. This is, for those of you wondering, this is suspect. These figures they're cooked up, but we're going to ignore that. Okay, so now we have an initial mass for our acid. And of course, that is enough information to calculate. It's enough information to calculate the moles. So this is really giving us the initial state for the acid. And we've already calculated the final state of the acid. So before I proceed any further, I'm going to write out our table once more. They gave us the reaction calcium carbonate. Let's write it here, calcium carbonate, and then ethanoic acid. And then to balance, 2 ethanoic ions, 2 ethanoic ions, 1 calcium, 1 calcium, 1 carbon, 1 carbon, and then hydrogens. 2 of them here, 2 of them here. Is that balanced? Yes, it is. Okay. Okay, so I haven't yet got the initial moles, but I know it has to do with this mass. And the final moles I do have 0.0145. Okay, so clearly, if I can get these moles, then I have to take the difference between these two, get this figure. I can mole ratio here, get this figure. I know that the acid was in excess, so calcium carbonate is the limiting reagent. I have nothing at the end. So if I can find the change in moles, that is the initial moles. It's numerically equal to the initial moles. Okay, so how I need to proceed is simple. I need to use this formula to find the moles of ethanoic acid. So let's calculate the molar mass of ethanoic acid. It is 12 for the one carbon. I've got 3 hydrogens, got another carbon, got 2 oxygens, and 1 more hydrogen. And that gives me 60 grams per mole. And now we get the moles. Put 4 decimal places down. No, that's wrong. It's 8. And this is what we can fill in over here. 0.188. And then we're going to calculate the difference. I'm going to put 4 decimal places down. Actually use the whole number here because I had it in my calculator. 4, 3. Okay, so I have the moles of the acid that have reacted. It is 2:1. So now I can mole ratio. It is 2:1. divide by 2, and I get I'm using the values. So I used the number. I didn't use this rounded off value. I just kept. I divided the value that I had in my calculator by 2. And now that I have the moles of calcium carbonate, I'm going to get the mass. This is going to be the pure mass. Why? Because they were asking us for a percentage. It's essentially a percentage purity. And here is the impure mass. So I'm going to get the pure mass now using this formula. Now this is molar mass of calcium carbonate. So let's find this. Okay, 100 grams per mole. And obviously I'm not actually using this value, I'm using the value that I had in my calculator. And I get 0.2. Maybe I should put down 3 decimal places. It actually doesn't make sense to put only 3 down because I have the other one to just 1 decimal place. But anyways. And now the percentage purity formula. Okay, so the percentage purity is going to be, total mass was 1.2. %. Done. This is going to be the last problem that we solve in this part, because this video is looking like it's going to be over 2 hours long. So a certain fertilizer consists of 92% ammonium chloride. A sample of mass X grams of this fertilizer is dissolved in 100 cubic centimeters of a 0.10 mole per cubic decimeter sodium hydroxide solution, NaOH. The sodium hydroxide is in excess. The balanced equation for this reaction is given, and then they want us to calculate the number of moles of sodium hydroxide in which the sample is dissolved. Okay, let's do that first. So we're given a volume and a concentration for the sodium hydroxide. This is going to be straightforward. The concentration is 0.1. The volume is 0.1. The moles is 0.20. It's 1/100. Okay, done. Now, before I read any further, I want to draw your attention to this. We're told that the sodium hydroxide is in excess. So you started out with some sodium hydroxide. How much? This much. And then you reacted it with the ammonium chloride. And you must have been left with some sodium hydroxide because it's in excess. Okay, so now let's read further. During a titration, 25 cubic centimeters of the excess sodium hydroxide solution is titrated with a 0.11 moles per cubic decimeter hydrochloric acid solution, HCl. Okay, so clearly, as I mentioned in the prequel, titrations, especially titrations that happen after a primary, the first reaction, the titration is a measurement device. So we have a measurement device here. It is used to give us information about this solution after the primary reaction. We started with 100 cubic centimeters, and this is a solid. The ammonium chloride is a solid. So when we add the ammonium chloride, the volume of the solution remains 100 cubic centimeters. During a titration, 25 cubic centimeters of the excess sodium hydroxide solution is titrated. That means, I made a comment about this in the prequel. When you measure your solution after a titration, you don't need to use the entire volume. It's actually better if you don't, because, as I mentioned, for two reasons. These solutions, they don't cost nothing. Like, money doesn't grow on trees. You don't want to waste chemicals if you don't need to. Right? Just don't waste. And the other thing is that maybe perhaps not in this case, but you might want to use your solution afterwards for something else. So you don't want to titrate the entire volume. You just need to pour out some of your solution and use only a part of it in the titration. And then whatever you know is true for the volume that you titrated, you can just scale that up to the entire volume. So we're breaking up the solution now. We're decanting it. You start with 100 moles. You were left with 100 moles of a depleted solution after this reaction. And then you only use 25 milliliters. So whatever, let's say we find a certain number of moles of sodium hydroxide that remain in this 25 mole solution. The moles that remain here are just 4 times as much, because the volume here is 4 times larger. Let's keep that in mind. Okay, so what are the details? During a titration, 25 cubic centimeters of the excess sodium hydroxide solution is titrated with a 0.11 mole per cubic decimeter hydrochloric acid solution, HCl. At the end point, it is found that 14.55 cubic centimeters of the hydrochloric acid solution was used to neutralize the sodium hydroxide solution according to the following balanced equation. There we are. Okay. And we are asked for 8 marks. Calculate the mass in grams, the mass X in grams of the fertilizer sample used. This is not necessarily hard. This is probably just long. And that's why we needed to spend time just trying to figure out where each piece of information goes. As I mentioned, we have an initial state I, and this measurement gives us the final state of the sodium hydroxide. They're asking about the fertilizer sample, which is this. So this problem is of the same type as we have been looking at during the rest of this video. Okay, so I'm going to start by drawing a table for the primary reaction. Need space. No, it made NaCl, ammonia, and water. And it was always 1:1. Okay, let's write this out. The initial moles of sodium hydroxide, we have that. The final moles, we're going to find that with this information here, this measurement. Let me simply write titration and multiply by 4. Okay, so we're going to use this information to find the final moles, and once we do that, we'll be able to calculate the change in moles, and then we mole ratio across to this number. This was the limiting reagent. We had nothing at the end, so whatever change we had, it must have been numerically equal to the initial moles of the ammonium chloride. They're asking us about the mass of the fertilizer sample. Clearly, if we have the moles of the ammonium chloride, then we can get the mass of the ammonium chloride. But they said that, so there's two things here we need to be clear about. There's ammonium chloride and then there's the fertilizer. The fertilizer is 92% ammonium chloride. So once we get this mass of ammonium chloride, we still need to apply one more piece of information. This percentage, essentially it's a percentage purity. We need to apply that piece of information to calculate X. Okay. So let us now go and find the final moles of sodium hydroxide. This is the goal now. We're given a volume and a concentration for the acid. Again, you can use the titration formula, and I would actually prefer to use the titration formula, but I'm not going to do it now. By the way, this is not for sodium hydroxide, this is for HCl. We will get to the sodium hydroxide after the mole ratio step. Okay, so we get and then let us use the mole ratio step. Now that is over here, because these moles of HCl we just found, they react with the sodium hydroxide. So we write the following. And now we need to say, how about this? And when we do this, we get okay, so we can fill this number in now. And now we can go and calculate the change in moles. Moles of sodium hydroxide that reacted is equal to the moles of sodium hydroxide that we had in the initial state minus the moles of sodium hydroxide that we had in the final state. The initial was 0.01 and the final state is this number. I get this. Okay, so this is the moles of sodium hydroxide that reacted in the primary reaction, which was this one here. We now mole ratio to the ammonium chloride. Actually, let's write this in here. Again, I don't expect you to write out this table. We're going to prove this. And now we need to get the mass. And the molar mass of ammonium chloride is nitrogen is 14, okay, almost done. We're trying to look for the mass, so and now we use the percentage purity. So this is the actual mass of the ammonium chloride that we just found. But the question was asking for the mass of the fertilizer sample. And the fertilizer sample we were given was 92% ammonium chloride. So 92 is equal to x is equal to okay, done. If you made it this far, thank you for your kind attention. There will be a part 2 in which I will discuss other types of problems. See you then.